Hi guys, welcome to the lesson of partial differential equations. So in the previous lecture, we talked about the classification of second order partial differential equations, and we talked about the function of three variables. That was z is a function of x and y. So the function of two independent variables, or in all we can call it the function of three variables, right? So now in today's lecture, we will talk about function of three independent variables or more than three independent variables. Let's say it's like this: u is equals to function of x, y, and z, or it may be like u is equals to function of t, x, y, and z. So we can see that this is a function of three independent variables. These are three independent variables, and this is the function of four independent variables. So we will learn how to classify the equations involving three or more than three independent variables. So for that, first of all, we will write the conditions. So let's talk about the condition number one, which says that if the eigenvalues, that is lambda I, are greater than 0, or lambda i's are less than 0, then the equation will be elliptic, right? So we have three classifications, that is elliptic, parabolic, and hyperbolic. So if the eigenvalues of the equation are all positive or all negative, so we'll call it as elliptic equation. And if one of the, if at least one of the lambda I is equals to 0, then the equation will be parabolic, right? So if one of the lambda I, any of the lambda, that is any of the eigenvalue is 0, so the equation will be parabolic type, right? And the last condition is that if one of the lambda I, if one of lambda I is greater than 0 and rest of them with opposite sign, or if one of lambda I is less than 0 and rest of them with opposite sign, so it will be a parabolic equation, right? Sorry, hyperbolic equation. It will be a hyperbolic equation. Right, so we'll discuss some examples in order to understand how to classify the equations. So let's take some examples. So let's say that we are given an equation that is del squared u is equals to uxx plus uyy plus uzz is equals to 0. This is basically the three-dimensional steady state heat equation, right? Three-dimensional steady heat equation, right? So we can see that the function of u depends upon three variables, that is x, y, and z. So this is a function of three independent variables, right? And in all, we have four variables, that is u, x, y, and z, and the independent variables are x, y, z, right? So now how to construct the matrix is, first of all, we have three independent variables, so it will be a 3 by 3 matrix. So first of all, in the first entry will be the coefficient of this uxx, right? So we may call it as a, right? And then it will be the coefficient of uxy, we can call it as b. Then it will be the coefficient of uxz, we can call it as c. Then again the coefficient of uyx, that is b again. Then the coefficient of uyy, that is d. Then the coefficient of uyz, that is e. Then the coefficient of uxz, that is c. Then the coefficient of uzy, that is e. Then the coefficient of uzz, that is f, right? So this is a symmetric matrix. We can see that this is a symmetric matrix, right? So actually, what is the idea behind it is that if we are given with the equation of three independent variables, this actually it can be written like this: auxx plus buxy plus cuxz plus duyy plus euyz plus fuzz plus gux plus huy plus iuz, and ju is equals to k, right? So this is the standard form of second order partial differential equation having three independent variables, right? So now we can see that this a is the first entry, this is the coefficient of uxx, this is uxy, this is uxz, again this is uxx, this is uh, or it's enough, I think, to understand that this is the coefficient and this is the coefficient of uxy or uyx. It's the same thing. This is the coefficient of uyy, right? This is the coefficient of uyz. This is the coefficient of uxz or uzx. It's the same thing. And you can see that c and c, because it will make a symmetric matrix. All right, so this is uyz and this is uzz, coefficient of uzz, sorry. So these are the coefficients, right? So in this way, we will construct the matrix. So now our equation is given as uxx plus uyy plus uzz is equals to 0, right? So we can make the matrix uxx is 1, uxy is 0, uxz is 0, uyx is 0, uyy is 1, right? Uyz is 0, Uxz is 0, Uyz is 0, and Uzz is 1. So now we can see that this is a diagonal matrix, so we don't need to find the eigenvalues because the diagonal elements itself are the eigenvalues. So the lambda 1 is equals to 1, lambda 2 is equals to 1, and lambda 3 is equals to 1. So we can see that all the lambda i's are same sign, right? So uh, in the upper part, we discussed that if all lambda i's are greater than 0 or all are less than 0, then the equation is elliptic type. So it's simple. We can see that this equation is elliptic, right? And it should be elliptic because when we talk about the Laplace equation, that was the two-dimension heat equation, two-dimension steady heat equation. So this is a three-dimension steady heat equation, and it's again the elliptic equation, right? So let's take another example. Say it's question number 2. So what is the question is that ut minus del squared u is equals to 0. So now we can, first of all, we can construct the original form. Del square u is basically uxx plus uyy plus uzz. So these all will become negative because of this negative sign. And now we can see that u is a function of 4 independent variables, that is t, x, y, z. So we can say that our matrix will be a 4 by 4 matrix. So we can construct the matrix in the similar manner. Then first of all, this is ut, but we need utt. So the coefficient of utt will be 0 because utt is absent in the equation. Then the coefficient of utx 0, uty 0, utz 0, right? Then the coefficient of uxt is 0, uxx is -1, uxy is 0, uxz is 0, right? Then the equation of uit is 0, and coefficient, sorry, 0, uxy is 0, uyy is -1, uyz is 0, right? Again, this utz 0, uyz 0, uxz 0, and uzz is -1, right? So again, it's a diagonal matrix, right? So we can see that the diagonal entries are itself the eigenvalues. So lambda 1 is equals to 0, lambda 2 is equals to -1, lambda 3 is equals to -1, and lambda 4 is equals to -1. So we talked about these types of equation. We said that if one of the lambda is equals to 0, then the equation is parabolic, right? At least one of the lambda is 0, then the equation is parabolic. So this is a parabolic equation, right? Now we will talk about the next question. That's question number 3. And it says that utt minus del squared u is equals to 0, right? Again, it's a function of 4 independent variables, and we can see that its u is a function of t, x, y, and z, right? So we can write in the standard form. So del square u is again equals to uxx plus uyy plus uzz. Again, the minus sign, these are because of this minus sign, okay? So now we can see that we have to construct a 4 by 4 matrix because of 4 independent variables, so we can do it easily. Now the coefficient of utt is 1, so it will be 1 here. It's 0, 0, and 0. This is utt, this is utx, this is uty, this is utz, right? Then here it's u tx, so utx is 0. Then here's uxx is -1, uyx 0, uzx 0, uyt 0, uxy 0, uyy -1, uyz 0, utz 0, uxz 0, uyz 0, and uzz is -1. So again, we can see that it's a diagonal matrix, so the eigenvalues are the diagonal entries. So we can see that now here we can see that one of the eigenvalue is positive and all other are negative. So we come to the conclusion that this is the third case, that is hyperbolic PDE, because we said that if one of the eigenvalue sign of the eigenvalue differs from rest of the others, so it will be an hyperbolic partial differential equation, right? So let's talk about another example. In fact, it's the last example. So let's say it's uxx plus 1 plus cx2 uyz plus 1 plus cx2 uzy, right? So now we can again see that this is an equation of function of three independent variables, right? That is u is depending on x, y, and z, right? So now we can construct the matrix form. So it's 3 by 3. So 3 by 3 matrix. Uxx is 1. Uxy is 0. Uxz is 0, right? Uxy 0. Uyy 0. And uyz is 1 plus cx2, right? Then uzx0, uzy is again 1 plus cx2, right? And uzz is 0, right? So now we can see that the diagonal entries, this is not a diagonal matrix, because other than diagonal entries are non-zero. So we have to work out for the eigenvalues. This implies that a minus lambda I, this is a matrix, a coefficient matrix. So a minus lambda I will be 1 minus lambda 0, 0, 0, 0 minus lambda 1 plus cx2, 0, 1 plus cx2, and 0 minus lambda. So now we can multiply to find the eigenvalues. So it will be like this, right? Determinant will be equals to 0. So I can write it as like this: lambda squared minus 1 plus cx2 whole squared is equals to 0. So I can say that either 1 minus lambda is equals to 0, or lambda squared minus 1 plus cx2 whole squared is equals to 0. So from here I can get lambda is equals to 1. So one eigenvalue is distinct and a real number, but the other eigenvalues are depending on the variable x2, right? So we will get two eigenvalues from this part. Lambda is equals to 1 time plus 1 plus cx2, and 1 will be minus 1 minus cx2 because of this square root. So now we'll plug these eigenvalues in the original matrix, or we can only work for these, because we just have to identify that either the lambdas are positives, negatives, or zero, right? So first of all, if 1 plus cx2 is equals to 0, which implies that cx2 is equals to -1, which further implies that x2 is equals to -1 over c. So what will happen to these two lambdas? What will happen to these two lambdas is lambda 1 will be equals to 1 plus c times -1 over c. So this will be 0. Again, lambda 2 will also be 0. C times -1 over c. This will be also 0, right? So, sorry, it's lambda 2 and it's lambda 3 because lambda 1 is already 1. So what we get is lambda 1 is equals to 1, lambda 2 is equals to 0, and lambda 3 is equals to 0, right? So this is the case of parabolic PDE, parabolic, with the condition that if x2 is equals to -1 over c, right? But what will happen if 1 plus cx2 is greater than 0, or 1 plus cx2 is lesser than 0, right? So from here we can find the condition. It says that cx2 is greater than 1, and it says that x2 should be greater than -1 over c, right? So what will happen to the lambdas when x2 is greater than -1 over c? So it will be 1 plus c times something less than -1 over c. When there will be something less than -1 over c in this part, let's say that it's -1 over 2c, right? Because -1 over 2c, sorry, greater than, x2 should be greater than -1 over c, so 1 over 2c is greater than -1 over c, right? -1 over 2c is greater than -c, so what will happen? C will cancel. This implies that 1 minus half, which is greater than 0, right? And we can check for other cases as well. C times -1 over 4c, because again this 4c is greater than this -1 over c. So again we'll keep on doing this, we'll keep on getting greater than 0. So lambda 1 is already 1, lambda 2 will be greater than 0. That means it will be positive, right? And what about lambda 3? Lambda 3 is equals to -1 minus cx2. So this will be, if I put -1 over 2c, so this will be -1 plus half, that will be negative. And when we keep on doing this, we will getting negative and negative. So lambda 3 will always be lesser than 0, so it will be negative, right? So what we conclude that two of the lambdas are positive and one is negative. So what's the case when one of the lambda is of opposite sign from rest of them? Then the equation we'll get is hyperbolic equation, right? So it will be a hyperbolic type. If, what's the condition? if x2 is greater than -1/c, right? So what if x2 is lesser than -1/c? So let's check lambda2 first. Lambda1 is 1, it's constant. So lambda2 will be 1 plus c times what will be x2 lesser than 1/c. So it will be like -2/c, -3/c, or something like that. So this will be -1. So this is negative. So, and when we keep on doing this, we'll always get lambda2 as negative, right? And for lambda3, it's -1 minus c times x2. And when again I will put something lesser than -1/c, so I can say -2/c. It will be -1 plus 2, which is equals to 1. It's positive. So when we keep on doing this, we'll keep on getting lambda3 is equals to positive. So we can see that two of the lambdas are positive and one is negative. So again, it's a case of hyperbolic PDE, because in hyperbolic we said that if one of if one of the lambda has opposite sign than the others, then the rest of ones, so that is hyperbolic, right? So this will be hyperbolic when x2 is less than 1/c or x2 is greater than 1/c. Both cases it will be hyperbolic. And for x2 equals to -1/c, but we'll get lambda2 is equals to 0 and lambda3 is equals to 0. So it will be a parabolic, right? We already discussed this case. Right, so this is all about the classification of partial differential equations having more than two independent variables. So we talked about 3 independent variables, and also we talked about 4 independent variables, and I hope you guys understand this topic well. So goodbye till the next lesson.